It's now, right?
Very good, yeah.
Okay, great. So yes, as Fritz said, please feel free to chime in during the talk. I would be very happy to make it interactive. Let me also start by indeed acknowledging a number of people. Fritz in the first place. This is a long-running project, and Fritz has been the main person there. I think he will also be very happy to chime in the discussion. So feel free to do that. Let me also maybe just to sort of keep track of the time. What is the sort of expected time for this talk? I can be flexible and improvise more or less, but it's good maybe to know a bit upfront.
So we normally do about 30 minutes with Q&A, and the schedule today is going to accommodate. You could do 30 minutes and then Q&A, or you could do 20 minutes with 10 minutes Q&A. It's entirely up to you.
Okay.
You've got flexibility.
I think we can easily talk an hour about this, so I'll try to sort of stick to the essence then. But feel free to interject if there's a timing concern. Okay, so let's get started. Maybe just to put this a little bit in context, I usually have these slides to sort of say what kind of research we do in Leuven. So I work at KU Leuven in Belgium, and over the I think we're in confidential computing already for a long time, for over a decade, and we have looked at almost all aspects of the system stack. So going from really application level development all the way down to the microarchitecture and everything that's in between, operating systems, compilers, and so on. And this project, I think, fits very well in there and is somewhat motivated by, as Fritz already highlighted, some of the attack research that I've done during my PhD. So just to make sure we're all on the same page, I have this very technical slide about Intel SGX. What is SGX? It's just a fortress inside the processor. Right? That's any type of confidential computing architecture. And we like to use this metaphor because the way you attack a fortress is by sort of targeting its weakest point. And very often it turns out that enclaves can be attacked from software via their interface. Just like you target the gates of a castle, you target the software interface of an enclave. And so you could say that this is the somewhat realistic depiction of academic researchers over the last decade attacking SGX. And just to sort of put that in a more scientific picture, this is a screenshot from the GitHub page of OpenEnclave. I think most of you are aware of this project. And you kind of see a continuous stream of vulnerabilities from very early when they went public around 2019 to very recent. And so realizing that enclave software, so there is a moving target. So there is continuously new types of attacks being discovered and new types of defenses that need to be implemented in the software. We sort of want to overcome that moving landscape. And so again, put this in a pretty picture. What TEs originally promised is to have a secure container for application development, and it turned out, of course, that in reality it's not that easy. And the first type of attacks that most of you, if you have programmed enclaves, might be aware of is pointer level vulnerabilities. So you have to really carefully make sure that pointers lie outside the enclave. More attacks have been shown at lower levels of the system stack, so CPU registers and configuration registers that are shared between these two walls. And of course, the most, I think, tricky attacks that have been shown are the microarchitectural attacks, right? that exploit bugs or shared components in the microarchitecture. And the overarching insight here is that all of these require or commonly require patches in software. Also, the microarchitectural attack landscape at the start was maybe this idle hope that this could be all handled transparently in software, in hardware, but more recent attacks, including LVI and Spectre and so on, require at least partial patches in software as well. And so that sets the scene. We need a way to validate that software is written correctly. We also need a way to sort of lower the burden on the application developer. And again, in a metaphor, what we want to do is to help the application developer bridge this treacherous bay securely from one side to the other. And that's where enclave shielding runtimes come in. So they basically offer a convenient abstraction to the application developer, the enclave application developer, that tries to take care of all these enclave-specific concerns. And I think being at the Confidential Computing Consortium, you're very well aware of this. Many of these now prominent projects that have arisen over the last decade are members of the Confidential Computing Consortium. I'm thinking of things like Gramine, the Intel SDK, and so on. So we have a very big landscape of different types of solutions, each with their own advantages and disadvantages, to do exactly this bridging over to the secure enclave application. And I think part of the contribution of Pandora, of this project, is to recognize that there is not one way of doing this, and there is an ecosystem of interconnected software, open source projects and closed source projects that do this. So Fritz made this very nice graphic on the left here that sort of visualizes this in a tree. And just to give you the high level summary, you can do this sort of at the function level by means of software development kits. Can also do this at the language level. Several languages, including Rust, have built-in support for SGX. Can also do this at the level of a full application, and then sort of give the library operating system abstraction. And of course, you can also do application development on those. And what we observe is that prior works on validation of Intel SGX enclaves have very narrowly focused on applications that were written with the official Intel SGX SDK. And as you can see, that's only it's a relevant but smaller subsection of the sphere here. And what we want to explore with Pandora is the negative of this landscape, and we want to explore sort of all the other runtimes out there. And importantly, we're less interested, it's not completely out of scope, but we're less interested in doing application level validation, because validating an application gives you one sort of certification of that application, but we want to validate the runtimes themselves, which is sort of the equivalent of the kernel in a normal deployment. So we want to validate those root of trusts at the software level. And the technical novelties we bring to achieve that, to achieve this big negative space, is a new way of loading enclave binaries into a symbolic execution framework. I will come back to that later. And also a way of sort of adding pluggable validation criteria of things you actually want to check. So in the rest of the presentation, I will try to just give you a sort of an intuition of these novelties that we bring. So let's start with this term. I already mentioned it a couple of times, symbolic execution. You may or may not be aware of that. I won't go too much into details, but I think most of you have heard of the idea. So let's say I want to validate that function on the top left. You could use something like a fuzzer, but it might take a very long time before it actually finds this magical number 1, 2, 3, especially if that's a large number. What symbolic execution does instead is it's going to sort of simulate this function. So it's not going to concretely execute it. It's going to execute it in a software model of the processor. And every time you do branch decision, it's going to keep track of that and sort of make an execution tree, which you see on the right. So it's going to autonomously explore and see that the whole space fits into 2 buckets with 2 different constraints on the if branch. So it's going to execute it once with a pin that is equal to 1, 2, 3, and once with a pin that is everything but 1, 2, 3. And does that, of course, in the backend with existing tools like constraint solvers. And so one way of, one very nice tool to do symbolic validation is Anger. Anger is an open source tool to do symbolic execution at a binary level for x86 and a number of other architectures, and it's written in Python. And so that's what we started using as a base for Pandora. Also, just to be fair here, we were not the first to use Anger to explore SGX enclave. So other works have done that. The most important ones are in the table here. This is a screenshot from the paper, which is publicly available. But without going too much into details, the main difference, again, is that they are very narrowly focused on application validation on the Intel SDK. And they also focus on, again, a rather narrow set of bugs they want to catch. And I think it's fair to say these tools are definitely valuable for catching bugs, but we're not really designed to what we call principle, to be principled, to sort of give you a type of guarantee when you would complete to a certain depth. And Pandora tries to overcome that both by being applicable to a wider range of runtimes and by yeah, giving you certain principled criteria to check. So just again, to set the scene, what is it that we have in mind with Pandora, had in mind when we started, is to not just make a nice academic tool, but also to make something that we hope will be used, that is usable to the extent that's possible, of course, within an academic project. So we fully open source this. I will get back to that later. We chose to do validation at the binary level. That's interesting because some prior works have done it at the source code level, and we found a number of bugs. For instance, one very tricky bug that was introduced by the compiler. So again, doing it at a lower level is interesting from a security perspective. We also hope that Pandora is not just a sort of a one-off tool, but more of an infrastructure to allow different tools to be built on top. And that's why we have this. From the start, we had in mind that we don't want to focus on one runtime, so we want to extend in terms of runtimes. We also want to extend in terms of what we call plugins, so the actual validation criteria. We hope that I showed you earlier that there's a number of different bugs and different requirements on software, and we want to catch as many as possible on that level as well. And ultimately, that's something that's more maybe still researchy, but ultimately we also hope that we can even abstract over architectures. For instance, we have recent results here in Leuven where we did the same on a 16-bit processor, so that it's not just x86, but it could be different even instruction architectures. And as I will come back to later, we hope that we can give you some sort of principled validation when the tool finishes, which is better than just bug finding. This is just sort of a sneak peek of how the tool looks. So this is the command line interface, which shows that it's as easy as just running pandora.py with a binary, and you can give it a number of different options to configure it. And the sort of output that it will spit out looks like this. So this is the command line output. It will give you a summary, nicely formatted of different issues it found. And also, importantly, it will link to human readable HTML reports, which look something like this. And so it has all the information that the symbolic execution tool produces. It can give you a disassembly if you click that open. It could give you the content, symbolic content of CPU registers, and even a full backtrace that tells you how to come to that vulnerability. So we found this greatly useful for ourselves when sifting through a lot of reports, and also the industry partners where we responsibly disclose the findings also found this very useful. So again, this is our hope that all the infrastructure can be reused if you want to implement validation for a different type of architecture or bug. So I said that there is these two novelties, so the principled validation and the loading of enclaves. Let's start with that, with the loading, and tell you a bit more about what is the challenge there and how we overcame that. So for those of you that have looked a bit at SGX in particular, it's a really weird type of extension, x86 extension, right? So for the operating system, it looks nothing like a normal binary, even if it's sometimes disguised as such. It sort of by design requires the operating system to be loaded very differently. Normally, the operating system does things like relocations, can write and read to the binary layout as it's loading the binary. With SGX, of course, you have to work more closely with the hardware. So there are certain pages reserved, memory regions reserved to interact with the hardware. Things like TCS is a thread control structure. You need one of those for every entry point in your application. You also have special areas where registers are saved on interrupt. You also have special metadata regions like this SECS and so on. And the bottom line that we observed when we started diving deeper into all this for Pandora is that all of these different projects, the ones that I showed on the screenshot before, many of those who are part of CCC, basically have made their own ad hoc abstractions around that. And so if you look at a binary for, let's say, Grammine, that will be very, very different from a binary for the Intel SDK. It will again be different for Microsoft OpenEnclave and so on. So a challenge that we faced before we could even start doing this work is how are we going to parse the binary? How are we going to make sure that we can load this binary into our symbolic execution infrastructure? Yeah, so that's summarized here in this slide. And so the solution we came up with eventually is that we just execute the binary once, and we're gonna listen in while we execute the binary once with a special tool which we call SGX Tracer. And SGX Tracer is based on the excellent ptrace system call infrastructure in Linux. So essentially, we're going to execute the enclave application once and listen in on system calls it sends to the underlying Linux kernel. If you look a bit more in detail, the system calls that we're interested in is, of course, the interaction with the SGX driver. And essentially, this kind of neat trick allows us to automatically discover when an enclave is being created, and then to listen in on all the pages, both the metadata and the data that is being added to that enclave, all that is being created. So what we do is, while the SGX driver, the Linux kernel infrastructure, creates the enclave by talking to the hardware, we sort of make a shadow enclave and write that to what we call here a memory dump file. And then we also write layout information to a JSON file. And this allows us then to simply parse this information and load that directly into Anger. And we can recreate the exact binary bit identical layout of the enclave with all of this information. And so Fritz wrote a very nice loader that is integrated into Anger to do exactly that. Fritz also wrote a number of extensions to the memory model that Anger already has and makes it aware of enclaves and the region that an enclave occupies in the virtual address space. So we made a number of what I think are really neat extensions to Anger to essentially make it aware of SGX. We also implemented the missing x86 instructions and yeah, that sort of makes sure that we can start executing an enclave in a way that we call truthful. So it will execute the enclave in exactly the same way as a hardware would. So it would jump to the very first instruction in the enclave and not cut corners as prior work has done, because they were interested only in applications that are in a much later phase. I want to dedicate a bit of our time also to some ideas that I've been discussing more recently, which is whether the insights and the work we have done for Pandora may be generalizable sort of for the ecosystem in more general. And I think the CCC is maybe a nice place to discuss that. So several years ago, I also had this paper together with Fritz on a case for unified ABI shielding, where we said that a lot of these runtimes in the SGX ecosystem are doing the same work in their own way, right? And I think there's an opportunity possibly for code unification, which comes with obviously security benefits because you don't have to maintain different code bases. And so just to sort of clarify the problem, I think, is that every project has their own abstraction around the hardware representation of SGX enclaves. And one way of overcoming that, I think, is a work that is already done by Fortanix, so the people who did also the integration of SGX in the Rust compiler, where they developed what they call an SGX stream format, which is essentially, I think, very elegantly captures the hardware semantics of an enclave. And the way it does that is by essentially relying on attestation. So the attestation mechanism that's built into the hardware for SGX already sort of needs to know the entire enclave content plus layout. And the way it does that, that's illustrated in the figure from an Intel slide here above. The way it does that is it will have it will sort of interleave metadata sections with data sections and do a hash sum over all of that. So for instance, a metadata section is EAT. So that's the EAT instruction. That's all the information you need to say there is going to be a next page here. There's going to be a page is following. Then you do a number of extends, which contain the data that should be loaded inside that page, followed by another EAT when you're at the end of the page. And if you just sequence that out, you get essentially a .txt file or so with all the data in there. And if you do a hash sum over that, you get exactly the Mr. Enclave, the measure enclave value that is being used in remote attestation. So the interesting property is that we now also have support for that in Pandora. It's not entirely upstream yet. But the interesting property of that is that we can guarantee that we do symbolic execution on exactly the binary as it is being attested to the remote stakeholder. And that's a property that prior works don't have, because they need a lot of hacks, and essentially they symbolically execute a different binary than the one that's being attested. So I think it's maybe worthwhile to discuss in its own right, but I think thinking about whether all of the open source infrastructure that deals with SGX enclaves could not benefit from a unified format is worthwhile. And you could even think of the driver. The driver could take as input, the Linux driver could take as input a .sgxs file and just load that in. That would be a different type of abstraction than the very low level abstraction you have now in the driver, which is essentially wrappers around the instructions. So you have a system call to do EAT, a system call to do extend, and so on. Yeah, if people have opinions on that, I would be very happy to discuss. If not, I can continue, and we can do that at the end, of course. Yeah, I told you earlier that one advantage of adopting this SGX stream format is that you inherit all of the tooling that already exists. So Fortanix wrote a number of very nice tools, and here you see the info tool that just summarizes an SGXS file, and here you see the point that I made earlier, that the layout of a Grammine enclave differs fundamentally from the layout of an SDK enclave. So for instance, you see Grammine has an unmap page at 0, and then it has a number of different read and executable pages. And you see that's very different for the SDK. There's also a different amount of entry points and so on. So again, all of this complexity is dealt with transparently by Pandora, because it just imports an SGXS file and doesn't care which runtime produced it. So let's go to maybe the more interesting part, which is how do you actually detect vulnerabilities? And that's where this plugin scheme comes into play. So essentially we have that engine component on the left. After the loading phase is done, which is, the loading phase is on the left and the engine component is in the middle. So after the loading phase is done, the engine will just talk to Anger and expose certain interesting events to plugins. So we have this idea of breakpoints, which means that a plugin can subscribe when it's being registered to certain events. For instance, I want to be notified whenever an enclave is being entered, or I want to be notified whenever an enclave accesses a pointer that lies outside its address space, and stuff like that. And our idea is that a plugin could really focus on the essence of the security properties it wants to safeguard, for instance, which typically are invariants. For instance, it could say this enclave should never access memory that's outside the protected region. That would be very easy to express by registering on pointer events and then validating that certain properties are true. And so any violations, again, are reported sort of in an abstract fashion and then automatically aggregated in these HTML reports. So plugins really only focus on the security properties, the invariants they want to validate. Typically, there are only a couple of hundred lines of Python. And so we developed 4 of these plugins. I will maybe in a selected fashion go over a couple of those. So we have that for the level of CPU registers, for the level of pointers, even for these more recent exotic things like memory map IO vulnerabilities where pointers need to be aligned. and also for control flow. So let's just say very briefly, what's the point with pointers? This is a very simple example of sort of an echo binary. Echo takes a pointer as an argument and it prints that out. It sort of returns that to the attacker. What could go wrong? Very simple. You point the argument to somewhere inside the enclave, and if the enclave, the software, does not have extra validation logic to make sure that this doesn't happen, it will just print out whatever that is being pointed to. This was a real bug in a very early version of Gramine that we found in research several years ago. So this can really happen. Things are even worse if you think about how do you validate a complex argument that consists of several pointer-to-pointers. Things get really, really messy very, very quick. I won't go into the details, but you have to check whether the first pointer lies outside. You have to copy it inside. You have to check whether the second pointer lies outside. And this can get very tricky very quick. And again, this is a study we did in 2019, and we found these issues in the whole ecosystem, production as well as research. We classified them in different instances, but essentially these are all pointer vulnerabilities. And so Pandora tries to overcome this full class by having an invariant that attacker tainted pointers. So it has a notion of taint tracking that we build into Pandora. So there's a notion of taint tracking, and it says any pointer that is partially controlled by the attacker should point to unprotected memory, should point to memory outside of the enclave. We use the constraint solver and together with our taint tracking mechanism to make sure that's the case. That works very well. It has a number of false positives. For instance, you could think of an array index where the attacker controls the index. If on the condition that you do bounce checking, that would be fine. But Pandora would regard that as a false positive, which we catch with a number of heuristics. So there is sort of a best effort, best effort classification for those, which works very well in our experience on many runtimes. Again, the output looks something like this. So let's zoom in a bit on that. You would have an address, and you see that this is partially tainted by the attacker, namely the value of attacker mem at a certain address is used in the computation for the final address, and you see what is the possible range of the pointer. You see that it can lie inside the enclave, and thus you're reading an enclave that's an address that was probably meant to be outside but can lie inside. You can find more details if you would click open the disassembly and so on. Another type of issues lies, I already mentioned that a couple of times, lies at the level of CPU registers. And this is work I've also done with Fritz several years ago, where we showed that this can get very tricky very fast again. So you would have a lot of registers in modern x86 processors related to vector instructions, FPUs, and so on.
Maybe we're already at half an hour. So I don't know if Dan wants to ask a question or if whether that's just a polite reminder of the time. So let's maybe skip to the results or speed up into the results a little bit. And then I guess we also have some time left a little bit for some questions if there are some on how to use Pandora or what it can be used for.
That sounds great.
Yeah, I was by no means being polite. I try to avoid ever being polite. I just had a question. In one of like the verbal list of things before you went into these more specific examples, you mentioned that you could trap on the enclave requesting or following a pointer outside of its memory space. And I'm curious what that event looks like that you're able to actually trap that.
So this relates to what I briefly mentioned in this slide. So there is an enclave, symbolic enclave memory model inside Anger. That's something that we added, that Fritz coded. And the way that looks is that every time when a memory address goes through the sort of through Anger's memory bus, Anger has also a memory bus, it simulates a processor. So every time it goes through that, Fritz wrote a piece of code that checks whether the pointer falls inside the fixed range of the enclave. An enclave in SGX is a fixed subset of the virtual address space. If it falls in there, and you use a constraint solver for that, because it could be a symbolic address. So if the constraint solver can tell you that for sure in all of the cases, I cannot find any counterexample where it does not fall outside of this range, then it's a protected address. Then we know for sure it's always inside. If the constraint solver responds that there are cases where it falls outside as well as inside, we trigger a certain breakpoint. If the constraint solver says it always falls outside, we trigger another breakpoint, and enclaves, plugins can subscribe to any of these breakpoints. And so the classification of where it falls happens in this memory backend. And plugins can just subscribe to any of these breakpoints and validate certain extra criteria. Does that make sense?
Yeah, it does. Thank you. And now I know that Fritz wrote that, so I can go pick his brain later if I want to dig in deeper.
Yeah, the code is also fully open, so you're very welcome to look at the code and even have critical comments or pull requests. We're happy to do it. I think Fritz is right that we're running short on time, so I'll just skip to the results, which are here. I won't go into details, but you basically see that we found a number of issues in number of runtimes all over the place. That was our research hypothesis, right? So that's for us, that's good. And I think also for the projects, because we responsibly disclose this and so on. In conclusion, I will point you to this github.com Pandora TE, where we want to host this project and where it's there. And the key novelties is to do this for the first time, I think, truthfully, so really following the behavior of the processor, that really led to very tricky bugs that other tools could not find, for instance, in initialization logic. To do this in an extensible fashion with plugins. We also have some work on, as I mentioned, on doing this even beyond SGX. And yeah, I think there's still plenty of bugs to be caught in the whole ecosystem. And hopefully Pandora can help to some extent with that.
And maybe to pitch in on the last sentences there with some of the kind of additional words. Like our conclusion of the whole project, I think to some degree, is that it is indeed practical to run some sort of automatic validation on, let's say, important and core pieces of the code regularly, right? So the runtimes that we talk about here, where I think the longest run I did was like 8 hours, and what was it, 60 gigabyte of RAM or something like that, just because we didn't have a bigger machine. But if you take a bigger machine and let it run for a day, I think you can get to reasonable big coverage for these small pieces of TCB that are as crucial as enclave entries or important pieces of code that do all of your legwork. Of course, if you then go deeper and deeper into your application, if you have some actual Linux running in there or something, of course, that's gonna be very quickly be a situation where you have to deal with state explosion. But for your important entry pieces, your low-level code parts, it is very feasible to let this run once per release or every few weeks or so, with a very conservative for 2024 standards budget. And so we hope that this is either a starting point or even just a tool that you can already use, but at least some initiative to talk about. You can do more nowadays than maybe you may think of when you hear the word state explosion. So these things are not impractical anymore, and at least for some core pieces you can run with.
Related to that also, we did find, and the details are in the paper, we did find a minor regression in Open Enclave where an issue that we reported in prior work in around 2019 was patched. And then with Pandora, we just discovered that it was unpatched by accident when patching another issue. I think that's, in our opinion, that's strong evidence for what Fritz outlined, that on release you could just run this as part of your validation and catch any regressions.
Exactly. Right, thank you, Jo. I'm happy to open this for discussion if anyone has questions, and otherwise I think he's there. I put the email in chat and check out the repo. Alec, go ahead.
Yeah, this question is coming more from the perspective of a plumber rather than a researcher, but I'll ask it anyway, and you can tell me whether or not it's appropriate. I have contact with some of the folks who are committers on OE, but I'm not clear from the presentation on the paper, just because I don't have the technical depth to understand it, whether this, whether Pandora would help with OE committers, or whether it would only help with the artifacts that are built using OE. I mean, I'm thinking, okay, so fine. If you're an OE committer, I'm sure they have test suites that run and produce applications that are built using OE, and they could run this on the applications, but I'm not sure if that would just find flaws in the testware or if it would find flaws in OE itself.
Yes, that's an excellent question. If I get your question well, if I understand your question correctly, I think the answer is yes, you can find issues in OpenEnclave itself, and we're less interested in validating applications built on top of OpenEnclave. There's prior works that arguably are better suited for that because they just they sort of dedicate the computational load more towards the application by skipping the runtime itself and sort of assuming that OpenEnclave itself is secure and will be coded well. We do the inverse, and we do the negative of that space, and that's what you see in this slide. So there is a number of applications, for instance, the more recent Signal applications are built on top of OpenEnclave. We didn't run those. We ran the sort of the core OpenEnclave itself, and we found several issues in there. So I think OpenEnclave is a nice project. They have tests, but those tests are more unit test fashion. What I think Pandora can do is more principled in the sense it's also less maybe performant, but in the sense that it just tests that the entire code base fulfills a certain invariant. And we found several violations which we reported and got fixed in OpenEnclave using that type of, let's say, validation methodology. Does that answer your question? Is that a correct understanding of your question?
I think it did. And let me ask a practical follow-up question. You threw some findings up there that included Radhika's contact information, some of the CVEs that were found. I'm wondering if you've been in touch with Radhika already, or if maybe I could facilitate an introduction.
I didn't catch the name. What is Radhik?
Radhika, sorry. Some of the CVEs that you mentioned that Pandora found in OpenEnclave, she responded to those CVEs in the public statements. That's Radhika, and I didn't know if you'd contacted her based on those findings, or if you've never had occasion to mutually be introduced.
We had, I don't know, Fritz, if you remember the name of the people, but we had excellent communication, I would say, with Microsoft people. The issues got resolved. I think communication was clear. So we've had...
Yeah, so I actually met her at CC Summit. We haven't chatted before, indeed, but I finally met her at CC Summit. And I think, if you can make the introduction to you, it would be, I think, always appreciated to just say hi. But CVE-wise and reporting-wise, that was kind of just via the open channels and via the visual parts. Sure,
makes sense. Well, I'll forward the paper to her just for her reading pleasure and facilitate an introduction. Thank you.
Thanks.
This has been a great presentation. A lot over my head, but I enjoyed it nonetheless.
Glad to hear.
Yeah, so it's sort of like a related thing that stuck out to me. I thought it was cool to see not just OpenEnclave, but Gramming and Keystone, which are also CCC projects. Another project that I didn't see on here that's kind of like a cousin of Gramming is Oaklum. And I wonder if they would be interested as well. So
Oaklum is on the was in the list there. Oaklum is in there.
Was it?
Yeah, we also have it in our table. I'm skipping to that. So we found I think we looked at Oaklum for the left column, but we only found derivative issues that were already sort of fixed in the Intel SDK database. On I think the problem is that's a limitation I think we should acknowledge. Pandora uses symbolic execution, which has state explosion, and Oaklum, we tried very hard to go deeper, but you have to first go to Intel SDK and then. But it's a nice project, I think. It's definitely in the scope of what we look at. We have in the past reported to them a CVE, a vulnerability they had, which we found with manual source code revision. So yes, I think that it would be interesting to look at it more systematically with Pandora, but it would need probably some novel tricks.
And to maybe also bring that part up. So I don't know if the situation is different nowadays, but we are now not actively working on Pandora anymore. So I moved to NVIDIA. I think you is onto other projects. That's a typical thing with academia, is that you write a paper, you try your best, and we also tried our best to make a tool that actually works and that you can actually run. But then afterwards, there's not much in it for academics anymore. Then so we move on to different projects. But if there's interest from the community, for example, to actually use this, to build on it, to reuse it or something else, we also talked about this, and we are happy to, I don't know, support it or talk about bringing it into the CCC if there's people that want to use it or something like that. I think we had different discussions on similar things like this before, but that doesn't make sense if there's no one that would actually want to use it, right? So we're very happy to discuss this and see if shopping around, if there's someone that wants to build this into the pipeline, extend it and look at it. Or even if we don't want to go that far, just to like look at issues and help support it, right? So there's definitely, if there's interest, please let us know, and we're happy to discuss it.
Yeah, fully agreed. In terms of research, I am looking with some master students. So yeah, there's limited manpower or people power, let's say. But I do hope to continue doing research on this. Of course, research goals are somewhat different sometimes, but I'm very happy to look together if there's an industry partner who wants to do some concrete things here. Invitation is open at any time in the future or now.
Yeah,
also,
I think that's really interesting. So Sal is our technical community architect, and Sal is on the call right now. But we kind of look for things where we can maybe help do some matchmaking in the community. And since this project touches, I guess, 4 different CCC projects, it might be nice to see if we can kind of get everybody either in pairs or in a collective meeting and talk about if there might be some joint interest in maintaining this through the CCC.
I would be very interested to, even if it's just exploratory, sit together for that. Also, maybe for some context, I forgot to say that during the talk, I recently met the people behind Anger, which is also an open source project from academia. I met them at an academic conference, and they were interested to merging some of the SGX support in upstream Anger. Again, people power, but I told him that I will look into that from September onwards and possibly work together with them to also have some of that supported by Anger, which I think would also be good for the ecosystem. So yeah, exciting developments.
Yeah, that sounds interesting too. And that also reminds me that we had a time of check, time of use tool presentation. I think it was around this time last year, maybe a little later in the fall, from an Intel author. And so I kind of also wonder if that would be interesting to loop in here. It was a very different approach. So it might be just kind of 2 subject matter related tools, but not close enough in architecture to merge into the same project, but that might be worth dusting off as well.
I would be interested to just hear about it. So if you have a public reference on it, feel free to forward it. Yeah.
Okay. Yeah, I'll make a note to myself.
Thank you.
Okay, and that's probably about time then for this topic. Any last question from anybody? Okay, great. Well, Fritz did not oversell that at all. It's rare that we get a topic that comes in and touches actually 4 of our projects. So I think this was a perfect tech talk subject. Really appreciate you coming in, Yo.
Thank you so much.